Welcome to our study of electrical circuits. The important quantities we're going to learn about when we study electrical circuits are potential difference or voltage, current, and resistance. We'll first study each of them separately, and then we'll put them all together. Let's begin with a review of potential energy, which you learned about last semester. Potential energy is the energy that is stored due to the positions of objects within a system. Now, we don't actually talk about potential energy itself. All we calculate is the change in potential energy, since the reference point for potential energy is arbitrary. And the change in potential energy depends on work done with or against a conservative force. If work is done with the force, that is to say the motion of the object is in the same direction as the force is pointing, then the change in potential energy is negative. You lose potential energy. However, if work is done against the force, that is to say the motion of the object is in the opposite direction that the force is pointing, then one gains potential energy for the system. For gravity, in a uniform gravity field, the change in potential energy is equal to mg delta y, where delta y is the change in the vertical position. Consider a cylindrical conductor, as shown here. And we know that conductors are objects that allow charges to flow through them freely. In our examples, we are going to treat the flow of charges as the flow of positive charges, although we know that in metallic conductors, it's actually the negative charges that do the moving. Now imagine that we place some excess charges at one end of our conductor. These charges now have potential energy because of the mutual repulsion of the like charges. In order to know how much potential energy they had, we would have to compute how much work was done against the electric force in bringing the charges to this location. This is similar to what we learned about gravitational potential energy. Whenever work is done against a conservative force like gravity, then you add potential energy to the system. So if I take this Hot Wheels car and work against the force of gravity, lifting it up here to this height of this hill, I have added potential energy to my system. The potential energy was independent of the path we take from one place to the other. The potential energy we give our cars depends on the masses of the cars, as well as the local gravity field strength and the height to which we lift the cars. The formula is the change in gravitational potential energy is equal to mgh. Each of the cars, because they may have a different mass, may have a different potential energy. Instead of calculating each car's potential energy separately, we could calculate the quantity g times h one time, and then multiply that by whatever mass we raise to that same height. The quantity gh is an example of what we call a gravitational potential difference. If you want to know how much energy we are adding to the system, we just have to keep track of how much mass we put through the potential difference of gh. The gravitational potential difference is defined as the change in gravitational potential energy per kilogram of mass. In this case, since the potential energy change was mgh, the potential difference is just mgh divided by m, or gh. With the Hot Wheels cars, the amount of potential energy added to the system depended on the mass of the car, as well as the height to which it was raised and the gravity field strength. When a charge is placed in proximity to other charges, the change in potential energy depends on the amount of the charge, as well as other details of the location where it was placed. Imagine bringing in another charge from a long distance away. Doing this adds potential energy to the system. Just as with the Hot Wheels cars in mass, we can calculate the change in electrical potential energy per amount of charge being moved. This is the electrical potential difference. The electrical potential difference is the change in electrical potential energy per coulomb of charge. Because this quantity is measured in a unit called the volt, it is also called the voltage. 1 volt is equal to a potential energy change of 1 joule per 1 coulomb of charge. Let's consider our conductor with excess charges again. Because charges can move freely through conductors, those charges would spread out. As we have seen, excess charges move to the outside surface of a conductor. Once the excess charges are spread out in a way that no charge experiences a net electric force, the charges cease to move, except for the random motion that all particles do. This includes charges inside the conductor. A net force is required to keep the charges moving in one direction because they continually collide with the atoms of the conductor. This conductor is said to be in static equilibrium. Since there is no net electric force on the charges in equilibrium, no work will be done on a charge when moving it from one part of the conductor to another. Thus, there is no electrical potential difference across the conductor. In the next presentation, we will see how a battery maintains a potential difference in order to keep charges flowing in a conductor.